All right, so we're now on to our last topic on computation of derivatives for Math 1560 Calculus 1 at U of L for fall 2017. So in the last couple of videos we introduced the chain rule and we looked at some of the consequences of the chain rule. In particular, we looked at implicit differentiation in the last video. And in this video we're going to introduce the method for taking the derivative of inverse functions if you know the derivative of the function whose inverse you're looking at. We're going to be interested in particular at the derivatives of the inverse trig functions, but let's start with the basics and then we'll work our way up. So remember how this works. So somebody gives you a function. Okay, so we have a function f, and we want it to be 1 to 1. Okay, so remember that the way you define a 1-to-1 function is in terms of the straight line test. There's a number of ways to define it, but this is one way to do it. So one way that you know a function is 1-to-1 is if you look at the graph of that function, okay, the function never does something like this. Okay, so if it does something like that, it's not going to be 1-to-1. And so the 1-to-1 property, the way you define it is like this. If you know that, say, f of a equals f of b, so the only way that f of a can equal f of b for a 1-to-1 function is if a is equal to b, right? So what that says is it says you cannot have a situation like this where you have, so if this is a and this is b, right? Notice that f of a equals f of b. Remember, f of a, f of b, these describe the y values for your function, and we can see that there are two x values corresponding to the same y value. So we don't want to allow this, right? So this sort of situation here is something which is not 1-to-1. We want to look at graphs that kind of do something like this. So generally, with a 1-to-1 function, you're looking at something which is either steadily increasing or steadily decreasing, right? The graph is always going up or it's always going down, because if you go up and then you come down, well, then you're in this situation here and you get more than one y value for, or sorry, you get a y value that shows up for more than one x value. So we want to deal with 1-to-1 functions, and the reason we want to deal with 1-to-1 functions is we want to define the derivative, and the inverse. And the way we define the inverse is like so. So the inverse basically is this. If I know that y equals f of x, right? So the way you think about how you usually use a function, right? You've got your function, you plug in your x value, you get out the y value. Okay, we can do that. But a question that you might want to ask is, okay, I've got a particular y value that I know came from my function. I want you to tell me what x value it came from, right? So the inverse is given the y value. The inverse is what is going to allow us to recover the x value. And so you say that this statement here, that y equals f of x, that's equivalent to saying f inverse of y equals x, right? So in terms of, a graph like we have here, what that's saying is, let's say I choose a particular y value, right? Here's my y value, okay? And I go over until I hit the graph, right? And then I figure out what's the x value that it came from, right? So with the original function, I take the x value, right? So with f of x, I start with the x value and I work my way up until I hit the graph and I see what my y value is. With the inverse, we go the other way. We start with the y value, we head across until we hit the graph, and then we go down to see what the x value is. That's what the inverse is computing for us, okay? And so if we were dealing with something like this graph here, notice that I choose a y value. This is why the reason we want 1 to 1 is that if the original function is not 1 to 1, the inverse is not going to be a function, because I say, okay, here's my y value, and now I'm going to head across. What x value did it come from, right? If my inverse is supposed to be a function, I should have a unique answer to that question, but we can see that we get two different values, right? So we can't have two outputs for a given input, so we can't define an inverse if our function is not 1 to 1. When we get to the inverse trig functions, if you're thinking about, wait a second, we're going to define inverse trig functions. The trig functions are not 1 to 1, right? They keep repeating over and over and over and over again. They're very far from 1 to 1. How do you deal with that? Well, one way you deal with that is you just decide that you're not going to look at the whole function, you're not going to look at the entire graph, you're going to choose a portion of the graph and only consider the inverse for that portion. So what you're doing is you're sort of shrinking the domain for the original function, you're shrinking the number of x values that you consider. And if I only looked at that part of the graph, then I could define an inverse, right? Because now for this y value, my inverse would be a, right? I would ignore the b value because it wouldn't be part of the range for my inverse function. So we'll see some examples like that moving forward. Okay. All right. So how do we take the derivative of an inverse function? And by the way, let me also remind you that there's a couple of review videos on inverses. So if you need a little bit more detail on inverse functions and inverse trig functions, you can go back, you can look at some of those review videos. So how do we define the inverse, the derivative of an inverse function? There are some subtleties here that we're going to sweep under the rug, but let's kind of look at the basic idea. So let's suppose we are given a function f and it's going to have two properties. One, it's going to be 1 to 1 so that we can define an inverse, and two, I want it to be differentiable. I want to make sure that f prime of x exists. Okay, so I want a function with these two properties. We want to find the derivative of the inverse function, okay, f inverse of x. So how are we going to do this? Well, go back to this defining property right here for the inverse, right? Y equals f of x is the same thing as saying f inverse of y equals x. So think about what happens if I do this. If I do f of f inverse of x, right? Now I guess I should probably exchange the roles of x and y here, so let's do that just to make sure that things match up here. So let's say f inverse of x equals y is the same thing as saying f of y equals x. So f of f inverse of x, well, f inverse of x equals y, so that would be f of y, but my definition of the inverse says that f of y equals x, right? So f of f inverse of x equals x. Good. Okay. How does that help me? Well, now let's come back to how do we find the derivative? And there's a couple of ways to tackle this, right? So one option, using that observation that I just made, is to say, well, before I go ahead and find the derivative that I want, we start with f of f inverse of x equals x, which we had on the previous slide, and we take the derivative of both sides. So we take the derivative of both sides with respect to x. All right, so what does that get me? Well, what that gets me is, well, how do I take this derivative? I've got one function composed with another, so on the left-hand side, I've got to do chain rule, right? F prime evaluated at f inverse of x equals, oh, wait, what am I forgetting? Derivative at the outside evaluated at the inside. Then I got to multiply by the derivative of the inside. What's the derivative of x with respect to x? Well, that's just 1. Okay, so what does this give me? What am I interested in? I'm interested in this. So how do I solve for it? Divide by that part, right? As long as that part is not 0, then the derivative of f inverse of x is given by 1 over f prime of f inverse of x. Okay, so that's the formula for the derivative of an inverse function. Now there's a couple issues here that I'm not addressing, and I'm going to show you also one other way that you can do this. And we'll put it over here in a second. So one of the issues I'm not addressing is this argument, because I'm applying the chain rule. The chain rule only works if I know ahead of time that my functions have derivatives, and I don't know ahead of time that this inverse function has a derivative, so I'm assuming the derivative exists in order to calculate it. There is a way to show that it must exist, but it's a very difficult argument. We sometimes even skip it in our third-year analysis course. It's quite tricky. So we're not gonna go anywhere near that. The other thing, of course, is the derivative for my original function. It has to exist, but of course it also needs to be non-zero, otherwise I can't divide by it. So we need our function to be differentiable, and we need the derivative of our function to be non-zero. Now, let me show you one other way you could tackle this using what we know about the inverse function. We could say, well, okay, f inverse of x equals y. Right, so let y equal f inverse of x, so that x equals f of y. Take the derivative of both sides with respect to x, and on the right hand side we're doing implicit differentiation, right? The derivative of y, or derivative of f, evaluated at y, and because it's a function of y I have to multiply by y prime, and that gives me what? That gives me y prime, which, notice y prime is the thing I want. It's 1 over f prime of y, right? And of course y is f inverse of x, so these formulas are the same. It's just two different ways of seeing that you can obtain that result. Okay, let's do one quick example before we move on to the inverse trig derivatives. Oh, two quick examples. The second one, of course, we know how to do by the power rule, but it'll give us a good check to make sure we're doing things right. So I want to calculate the derivative of the natural log. Now, I've already mentioned, and we gave no justification for this, but we know, well, maybe in quotes no, because we haven't really convinced ourselves of this. We know that the derivative of the natural log is supposed to be 1 over x. So how do I see that derivative is supposed to be 1 over x? Well, what we do is we let y equal the natural log of x, and rather than using that formula I gave you on the previous slide, I'm going to follow the method I used to obtain the formula. So what I'm going to do is I'm going to use the fact that the natural log is the inverse of the exponential function. So I can take e of both sides, right? Saying that y equals the natural log of x is the same thing as saying that e to the y equals x. And now I can take the derivative of both sides with respect to x. So on the left-hand side, when I take the derivative of e to the y, I get simply e to the y. But because I'm taking the derivative with respect to x, implicit differentiation says I need to multiply by y prime. On the other side, I simply get the derivative of x, which is 1. And so that means that the derivative of my f inverse here is what? It's y prime, which is 1 over e to the y, but let's get that back in terms of x. What was e to the y? E to the y was x. Okay, and I've got my derivative for the log function. What about for the cube root function? We can do the same sort of thing. If y equals x to the 1/3, I cube both sides. Y cubed equals x. Right. So notice my g of x here is x cubed. Right. That's the inverse. And I take the derivative of both sides with respect to y, so I get 3y squared times y prime, and that's going to be equal to 1. So y prime is 1 over 3y squared. But what was y? Y was x to the 1/3. So this is 1 over 3 times x to the 1/3 squared, which is 1 over 3 times x to the 2/3, which is, as we expect from the power rule, 1/3 x to the minus 2/3. So it works. All right. So that's the general idea of the derivative for inverse functions. In the next few videos, we'll see how to use this to get derivatives for some of the inverse trig functions.